Greetings. My name is Taciroglu. I'm a professor at the Civil and Environmental Engineering Department at the University of California, Los Angeles. I'm also a faculty affiliate of the B. John Garrick Institute for the Risk Sciences. In this video, I'd like to present you a vision for regional performance-based seismic assessment of bridges, as well as some of our work in progress in this area. Let us begin with motivation and objectives. So why regional assessment? What does motivate regional assessment studies? As civil engineers, we routinely design structures, almost invariably one at a time, and in these design processes, we hardly ever consider the performance and behavior of other buildings and structures in the region. Nevertheless, hazards affect entire regions, and the proverbial big picture is needed for developing actuarial plans, for urban planning and for devising public policy decisions, and for emergency service planning. For each of these three items, the respective consumers of the big picture are insurance companies, government agencies, and first responders. Moreover, the built environment is highly interconnected. It comprises residential neighborhoods and business centers, transportation networks, and lifelines. These components interact with each other in significant ways and affect each other's performance, not only during extreme events, but also under service conditions. Now here's a scenario that highlights the issue at hand. Imagine a hospital building that is designed for the most extreme event, and imagine that such an event has happened and the hospital indeed remained operable, which is great. However, also imagine that several key bridges in the region have collapsed and a great majority of the hospital personnel couldn't get to work that day. Clearly, the performance of this emergency response facility simply could not be gauged through an analysis that ignores network effects. Now that we've established the need for regional assessment, let us identify the challenges. The first class of challenges involve harvesting of data and the conversion of data to metadata and eventually into analysis models. This is a challenging task because sample population is diverse. In other words, not all bridges and buildings are the same. And this diversity requires the use of sophisticated and as of yet non-existent data harvesting tools. Another challenge is that access to detailed data may not be possible. This would then require estimation of missing data through techniques such as machine learning. Finally, processing of harvested data and analyzing the resulting models require large computational resources. It is fair to state that regional PBSA studies will break computational records among civil engineering applications. The subsequent challenge involves transforming the models into decision variables such as economic loss estimates, downtime and repair costs, and insurance premiums. The challenges in this area include the necessity to use heterogeneous analysis tools and to link them. In the present context, these tools include OpenSeas for nonlinear structural analyses of models, OpenSHA to estimate the hazards, and FEMA's Performance Assessment Calculation tool, PACT, to estimate the economic losses. New methodologies need to be brought in, including data analytics and Bayesian inference methods, to organize and make sense of the output of the analyses over the extremely large metadata sets. Given the motivation and challenges cited before, the objective of the present effort is to develop a semi-automated interactive platform that can evaluate the seismic vulnerability of complex transportation networks. There are three distinct threads of features that such a platform should have. One, it has to be able to generate structural models. Two, it has to be able to carry site and structure-specific seismic analyses. And three, it has to be able to evaluate the consequent economic losses at the network level. Existing predictive computational tools and IT capabilities do allow unprecedented granularity for such seismic and loss assessment studies. Yes, the technologies and tools exist, and a few attempts have been made towards this goal, such as the study by Miller and Baker shown here on the left. However, the type of regional PBSA that we're aiming in our study, which features site, structure, and hazard-specific granularity, has not been achieved, nor even attempted before. So what is our vision and what is our scope? Here's a graphical illustration of the envisioned workflow for our regional PBSA methodology. We begin by developing an analysis model of a given bridge, for example, using images. We then devise a suite of representative ground motions for the specific site of our bridge. We use the model and the ground motions in nonlinear time history analyses in order to develop a statistical picture of the potential outcomes in the form of, for example, fragility curves. These fragility curves can then be used to estimate the decision variables for assessment, such as economic losses, downtime, repair and retrofit costs, or insurance premiums. We plan to carry out this workflow through a regional PBSA computational platform we're currently developing with my students at UCLA. The toolbox contains a module that harvests raw data, including images, from public databases and users, and converts them into metadata. These metadata are then stored and organized in a relational database. Using the metadata, it is possible to create analysis models, and the analyses are carried out using several publicly available tools. OpenSHA is used to compile site-specific ground motions from databases such as PureNGA West 2. OpenSeas is used for carrying out the nonlinear time history analyses which yield the fragilities. And FEMA-PACT is used to estimate the losses. Once the site and structure-specific results are computed, they are committed back to the relational database so that they can be accessed by users, and also they can be used to learn about the common behavior of subclasses of bridges and components. This learning process can be used to eliminate unrealistic and non-physical results, and also to devise automated metadata for yet-to-be modeled new bridges for which only a few pieces of information are known, such as structure type, number of spans, and year built. The final component of the regional PBSA tool will be its user interface, which will allow users to contribute data and to visualize the models and the analysis results. At the present time, we're configuring our tool to interface with Google SketchUp and Google Earth for visualization. Here are some of the details of the envisioned components for our PBSA framework. Let us begin by describing the image to model module. Let us in fact emphasize the fact that we will not only use images, but any viable available data to create the models required for our analysis. So where will these data come from? A good portion of the data required to devise bridge models for analysis will come from databases. One such major database is the National Bridge Inventory, which is compiled by the Federal Highway Association. This database provides metadata such as year built, construction type, and materials used for all bridges and tunnels in the United States. Its primary intent is to bookkeep bridge conditions. Another major database is the Caltrans Bridge Database, which is compiled and maintained by the California Department of Transportation. It provides all details of bridges, including foundation configurations. This database contains mostly analog data in the form of structural drawings, and thus it cannot be interrogated automatically at the present time. Nevertheless, it can be used with permission from Caltrans to validate and categorize image-based models. Another source is the California Strong Motion Instrumentation Program CSMIP database, which is maintained by the California Geological Survey. It provides structural and foundation details of 72 bridges in California. This database can be interrogated online, and it contains bridge response data from past earthquakes, which can be used for model validation. In our study thus far, we have already created computer codes that automatically extract all available information from the NBI and CSMIP databases. Some of the data will come from existing guideline documents. Caltrans standard plans allow accurate estimation of several metadata elements, such as abutment seat length, shear key reinforcement details, box girder details, and foundation configurations, by using other harvested data such as number of spans, number of lanes, and year built. Our master's and PhD students are currently making progress on developing data mapping systems to estimate unknown metadata based on priors and data dependency rules that we're extracting from Caltrans standard plans. Another similar and important source is the Caltrans Seismic Design Criteria Manual, or Caltrans SDC for short, which provides era-specific information on component as well as system design. Again, it is possible to extract metadata rules from Caltrans SDC and accurately estimate, for example, the column reinforcement ratios from other harvested data such as location, year built, number of spans, and number of columns. A major source of our data will be the internet, and the primary providers of these data will be the navigation and GIS tools such as Google Maps, Google Earth, and MapQuest. All of these applications can be interrogated online to extract images as well as topographic data. I will describe how we use these databases to develop our geometry models later. Another major source of data will be the general public, i.e. the users and viewers of our regional PBSA tool. We will use crowdsourcing techniques to extract information when it is simply too difficult to devise a computer algorithm to do the same job. To increase the reliability of crowdsourced data, we're developing a Wikipedia-style interface for our data contributors. The collected data will be reviewed by referees whenever possible, as well as machine learning algorithms to eliminate nonsensical entries. Here's an example of how crowdsourcing can be used. We can show a user what a typical seat-type abutment looks like. We then provide the user a photograph that shows the abutment of a particular bridge and ask if the user thinks that this is a seat-type abutment or an integral one. Let us now move on to the specifics of how images can be processed. Development of an image-based model begins with locating a bridge and marking its abutments. We do this by a combination of automated and crowdsourced method. We start by reading the approximate bridge coordinates from NBI. We then extract a satellite image of the location corresponding to the approximate bridge coordinates. We run a road extraction algorithm to detect roads on the selected image, and then generate random points on detected continuous road lines and pass the coordinates to the Google Roads API. We then cross-check road inventory with NBI and then highlight the relevant road line. We then prompt the user to mark the beginning and end points of the bridge abutments. We use a similar workflow to extract a set of images for the selected bridge and develop a geometrically accurate wireframe model of the bridge deck and its supporting columns and piers. A similar workflow generates the deck geometry and super elevation data. Determination of the column properties begins by locating the columns. For each identified column, we extract multiple images, such as north-facing, south-facing, etc., and determine the column type based on the number of detected column edges. For example, a consensus of only 2 edges observed from multiple viewing angles would mean a circular or an ellipsoidal column. Once the cross-section geometry is known, we sample the column height and width at a number of levels. Finally, we estimate the rebar detailing by interrogating a database of similar columns and by utilizing design rules and recommendations specified in Caltrans SDC. Now, the bridge model can be completed using crowdsourced data as well as metadata harvested from the databases. This step will yield information on the types of abutments, foundations, and shear keys. Refinements can also be made at this point by utilizing metadata rules learned from the Caltrans standard plans and Caltrans SDC using, for example, Bayesian inference techniques. These steps will ultimately yield a complete analysis model. For regional PBSA, in addition to a viable analysis model, we need site-specific hazard data. This objective can be easily achieved by using various existing tools such as OpenSHA, which ultimately enable the compilation of a suite of representative ground motion time histories for a chosen level or intensity of hazard. This compilation can be achieved in different ways, and in the ideal scenario, the ground motion time histories are produced by aggregating hazards from faults affecting the particular site, and by using state-of-the-art attenuation relationships that model ground motion propagation from the source to the site. OpenSHA and relevant ground motion databases had been developed through decades of coordinated research, which primarily took place at the Pacific Earthquake Engineering Research Center and the Southern California Earthquake Center. The present project is fully utilizing these tools and databases by interrogating them through the internet using properly devised scripts. With both the model and the hazard at hand, we can now carry out the analyses, extract the fragilities, and subsequently estimate the losses. So what does an analysis model comprise? In the analysis step, we'll make use of harvested metadata and create input files and scripts for the particular nonlinear time history analysis code that we will use, which is OpenSeas. In the recent past and through nearly a decade of sustained research that involved several field tests, my group and several other colleagues in California and Washington State have devised state-of-the-art validated models for bridge subcomponents. These include models for piles, abutments, shear keys, in-span hinges, and columns. The references in light blue are work from my group and collaborators. The culmination of these efforts are outlined in a recent report that we had submitted to Caltrans, which provides best bridge modeling practices for PBSA. This report and our experiences will inform the development of analysis models in the present project. The aforementioned analyses are not only carried out using a suite of site-specific ground motions, but also using a model matrix of the particular bridge structure that brackets the uncertainty in the estimated model properties, such as reinforcing details, foundation types, as well as geometry. These analyses will require many simulations, and a basic approach for this is to use the Monte Carlo technique. Because each model under a specific ground motion can be analyzed independently, the computations can be easily carried out on a cloud service in parallel with near-perfect scalability. The analyses will yield, among other things, the so-called IM-EDP curves, where IM denotes an intensity measure such as peak ground acceleration, and EDP is a response parameter such as column drift ratio. The uncertainties in these curves due to ground motion and model variabilities are captured as an inherent outcome of the Monte Carlo analyses. The analyses will also yield fragility curves, which denote the probability of exceedance of a pre-damaged state given the ground motion intensity measure. For example, here we have computed the probability of collapse of a bridge that has skew-angled abutments. The final, and arguably the most important ingredient in regional PBSA is loss estimation. Damage to a bridge leads to casualties and functional loss, which comprises direct losses such as repair costs and indirect losses such as downtime and casualties. Extensive research had been carried out for buildings, for example, to transform EDPs into direct and indirect losses. The results of these efforts have been packaged into the FEMA Performance Assessment Calculation Tool, PACT, which provides fragilities and performance functions for structural as well as non-structural components and systems. In the graph, we're seeing a generic FEMA performance function. The vertical axis is a probability of exceedance function. For example, probability of the acceleration of the second floor of a hospital building exceeding 0.4 g. The horizontal axis is the impacted quantity, for example, the repair costs of an MRI machine which happens to be located on that second floor. While fragility and loss functions for structural and non-structural components of buildings are well represented in PACT, they're non-existent for bridges. Our long-term plans in this area include trying to replicate the FEMA methodology for bridges, devising apps and tools for computing component fragilities which enable rapid post-event assessment, compiling repair and downtime data and statistics in collaboration with Caltrans engineers, and devising methodologies for network impact and recovery analysis with economists and urban planning experts from UCLA's Luskin Center. The broad description of our proposed methodology is complete. I'd like to now give you a couple of application examples. The first example is the development of a geometric analysis model for the San Bernardino I-10-I-215 interchange bridge, which is also known as the Colton interchange. We have studied this particular bridge because we were provided with access to as-built structural plans for this particular bridge, which enabled us to validate our image-to-model toolbox. Our automated road selection tool locates this bridge first by using the NBI data and highlights it so that a user can mark the abutments. The user can mark more than just 2 points, but only the outermost points on the highlighted route are used to delineate the bridge. By utilizing the user input, our program first calculates the curve corresponding to the bridge center line. This curve is typically sampled at 50 data points. Next, ground elevations and road elevations corresponding to each sampling point are harvested. Subsequently, the bridge center line data points and ground elevations are harvested using Google's road and elevation APIs respectively. And the road elevation data are collected through MapQuest elevation service. Our program then harvests Google Street View images associated with the selected bridge and automatically identifies the bridge bent locations. Once the bent locations are identified, the program automatically generates a wireframe model by utilizing the determined spine curve shape, elevation data, and the bent locations. Here's a comparison of actual measurements obtained from as-built drawings of the Colton interchange and the measurements automatically extracted by our image-based model generation tool. As seen, the accuracy is quite remarkable over the entire bridge. After the wireframe model, the program automatically identifies curves and spirals comprising the centerline geometry. By combining this information with speed limit data, the expected curve superelevation profile is determined. The next step is to determine the dimensions of the detected columns. For this purpose, our program goes back to the pictures utilized for detecting the bent locations. And by using fuzzy logic membership functions, it compares the intensity of neighboring pixels to detect the column edges. Edge detection not only generates an outline of the column shapes, but also establishes the cross-sectional shapes of our columns. Columns with internal edges are assigned a rectangular shape, while column elements without internal edges are assigned a circular shape. Once the column edges are detected, our pixel counter module samples the height and width of each column at intervals. Subsequently, by comparing the average column heights in pixels to the column heights determined in the preceding steps, column width profile is determined. In the example shown here, only a single pixel count process is depicted. In reality, our program evaluates each bent location from different viewing positions to establish a detailed data set. Here's our second example, which is a water crossing bridge in San Diego Bay, which connects the Coronado Island to the mainland. The process for this bridge is the same. The bridge is marked first by a user. The road and below water ground elevations are extracted next. The images are harvested, bent locations and column dimensions are extracted, and the wireframe model is generated automatically within minutes. Unfortunately, we could not validate this model because Caltrans could not release the structural drawings due to security concerns. We're currently in the process of applying our regional PBSA tool to a set of bridges on a testbed route. The said route is a 40-mile stretch of the Interstate 405 that connects the Port of Los Angeles to the San Fernando Valley. This portion of I-405 has 170 bridges, and we're developing analysis models for all of them for PBSA. We've already extracted their metadata from the NBI database, and we are in the process of extracting their geometries. This testbed study will allow us to debug our platform and validate its results. By modeling a few of the testbed bridges from as-built Caltrans drawings, we will be able to determine how accurate the image-based model analysis models can become. We anticipate concluding this phase of our project and present some of our results to the public by the end of fall 2016. I'd like to conclude my presentation by stating that in our group here at UCLA, we also have a fairly substantial effort directed towards the regional PBSA of buildings. Here's one of the buildings that we have developed an image-based model for, and we're currently focusing on multi-story reinforced concrete buildings. We have plans to extend this work to residential and commercial structures as well. This concludes my presentation. You can always reach me via email for questions and comments, and I thank you for your attention.